tapping a hole in a part is done on a lathe in very much the same way that it's done on a milling machine or a drill press. We started here by drilling a pilot hole in preparation for putting threads in the hole. I'll start by putting the part securely in the chuck. Because during the threading operation I'll be applying torque to the part, I start by locking the spindle. And on this machine I do that with this knob, pushing in until it clicks into place. And now, see, I've locked the spindle. I start by putting this little tool in the chuck to use as a pilot for supporting and guiding the back end of the tap handle, like this. It's also possible to use a regular taper. This is a live center, can also be inserted in the tailstock and used to support the back of the tap handle. We start by inserting the tap into the hole, then bringing the small taper into contact the back of the tap handle. Now I'm moving towards the back of the machine. This gives me a better position which to turn the handle, the tap handle. And while I'm turning this, I'm also applying just enough torque to this wheel to maintain contact between the taper and the back of the tap handle. If I don't keep up with this handle, what happens is that the tap handle unseats itself from the taper. At this point, it's very easy to break the tap. So make sure you maintain contact here. After several turns, the tap handle, it's a good idea in many materials to turn the tap backwards, about a third of a turn. This breaks the chips inside the tap and frees them up so that they can be forced out of the flutes that run up the side of the tap. After going in about half the length of the threaded portion of the tap, it's usually necessary to remove the tap from the hole to completely clear the chips. Very much the same way that you do when you're drilling a deep hole. Now you can see when I was removing just the last few threads of the tap from the hole, I was shaking the tap handle around quite a bit. If you're working with very soft materials, it's easy to damage the last few threads that way. So then it's a good idea when withdrawing the tap to remove the tap handle, then withdraw the tap by hand. We clean the flutes of the tap. And carefully start the tap. It's easy at this point to start the tap in the wrong direction and start producing another set of threads. If you feel the tap starting to bind at any time, you've probably started the tap incorrectly. You should back out and try again. Many materials can be tapped dry. To get a better finish, or to tap particularly tough materials such as stainless steel, it's a good idea to use a little bit of cutting fluid. You continue this process until you have completely threaded the hole. A drill will produce a hole in a part like this that's within a few thousandths of an inch of the nominal diameter of the drill. If you want a more accurate hole than that, a common way to achieve that is with a boring tool like this. This long, thin tool allows you to get down inside a hole like this and machine that surface. To set up the lathe for boring, start by putting the part in the chuck. Put the lathe tool in a holder like this. It clamps it securely. And this holder placed on the tool post and locked down. Start by bringing the end of the tool just inside the hole, and then with the cross slide, bringing the tool out until it's nearly in contact with the side of the hole. Spin the chuck to make sure that there's no interference between the part and the tool, or between the chuck and the rest of the lathe. Now I'll bring the tool out until it just contacts the inside of the hole. You can hear it making a very light cut. Now I'll back the tool out of the hole. Dial in the desired cut. In this case, all I want to do is clean up the surface of this hole. So I'll remove about 0.010 of an inch during this pass. This is an operation that's very difficult to control by hand. The variations in feed rate that you can't avoid when you're feeding by hand produce variations in the cutting force on the tip of the tool. These tools are typically very long and thin, so those changes in cutting forces produce relatively large deflections in the tool, which then change the diameter of the hole. So for any holes other than very, very shallow holes, it's best to get the tool set right, make sure the depth of cut is what you expected, and then engage the power feed for the saddle. Because you cannot see the end of the tool during the cut. It's very important to know how deep the tool is in the part if the hole that you're making is not a through hole. You can do this very simply and roughly by running the tool down by hand until it touches the bottom of the hole. A very quick way of setting some indicator of the depth is simply with a marker or a piece of tape that you can put on the boring bar at this point. And that way, during the following passes you make as you enlarge the hole up to the desired size, you can then disengage the power feed just before you get to that mark and then continue feeding the rest of the way by hand. Another more accurate way to do this is with a dial indicator. You can adjust the micrometer so that the dial indicator reads 0. Back the tool out, make another pass, and when the dial indicator starts to move, that's a warning that we're getting close to the bottom of the hole and it's time to stop the power feed and continue from that point by hand. Another common way of setting a stop for the depth of a hole is with a saddle stop, which is simply a clamp that attaches to the bed of the lathe and generally incorporates a micrometer adjustment like this. You can see after the first pass I've made with the boring bar that the finish the boring bar has produced is much better than that was produced with the drill. The hole is now very round, but not yet to the final size. So we now measure the hole we've made. And then using the dial on the saddle, we can enlarge the hole until we reach the desired size. This tool is not very stiff, so you can't take a large cut. So typically, you have to enlarge the hole in several steps until you approach the final size. When you're very close to the final size, say within 5/1000ths of an inch, it's a good idea to take a very light pass, remeasure the hole, and then take a final pass of a few thousandths of an inch. Knurling is often used on tools such as this center punch or this drift to improve the grip you have on the tool. You can hear, if you look closely, you can see there's this little diamond pattern over the surface of the tool. This pattern is produced with this tool. This tool is inserted in the lathe and then brought up in contact with the part and then fed down the length of the part. There's some fairly careful setup that's required initially to get the angle of the tool set right this way and also the height of the tool. I'll bring the tool into contact slowly. And then have a look at the pattern it produced. Now, if you look closely here, you can see that the tool is offset slightly from being perpendicular to the part. So the tool is cutting in deeper at this edge than at this edge. That's about the right angle we want. So we're going to plunge into the part this way and then feed down the length of the part. If you look very closely, you'll see, though, that rather than a diamond pattern with cross-hatching there, only one of these rollers has come into contact. That's because the height of the tool isn't set quite right. You want to keep adjusting the height of the tool until you get a uniform crosshatch pattern. Okay, now both wheels are coming into contact with the part. We are getting a uniform crosshatch. Now I plunge the tool into the part and wait for several revolutions for the teeth to settle down into the part before engaging the feed. Now you can see the tool feeding down the part, leaving the knurling behind it. Not so good. What's happened here is that the wheel producing these grooves settled down into a uniform pattern. But if you look at the cross-hatching, you can see that the wheel in the other direction is actually producing about twice as many grooves per unit distance that this wheel is producing. Now, you will get this behavior, if you think about it, in almost every case, because unless the wheel diameter is a multiple of the diameter of the shaft, in one revolution, this tooth on the wheel won't come back to exactly the same place. And the way to avoid that problem is to plunge quickly enough so that you produce deep grooves during the first revolution, deep enough so you form V's that allow this wheel, even though it's not going to register exactly, to catch the V produced in the first revolution and then fall down in place. And after several more revolutions, some averaging takes place so that the wheel produces uniformly spaced grooves around the part. So we'll try again. I'll come in a little faster this time. Okay, much better. You can see here that this pattern is symmetrical as it is on this center punch, and this is the desired effect. The compound on the lathe is often used for cutting tapers. To do this, we start by loosening the bolts that secure the compound to the cross slide. See here, the base of the compound have degrees marked out. So we rotate the compound to get the desired angle. Lock the compound in place. And use a tool that is typically the same tool that's used for turning. Before you begin the cut, advance the compound to the limit of its travel so that you make sure that when you finish the cut, you haven't used up all the available travel in the compound. Back the compound off until you clear the end of the part. Start the machine. And with the compound and cross slide, adjust the tool until you're taking the desired cut. Now with both hands on the crank on the compound, it's possible with practice to maintain a fairly constant speed. You can see after making this first pass that we still have plenty of travel till we run to the limit of the travel of the compound, which we will need as this feature becomes wider. Take another cut. And you continue in this way until the feature has reached the desired dimension. turning long, thin parts, such as this one, can be a problem due to the deflection of the part due to the cutting forces produced by the tool. I'll show you what that looks like and sounds like. If I try to take a pass in this part, you can hear the noise, the chatter. And if you look closely, you can see a very irregular surface finish. What's happening is, due to the deflection of the part rises up a little bit, rides up onto the tool, and then back off the tool and vibrates. In order to deal with this problem, start by machining a center to the end of the piece. Now have the center machined into the end of the piece. You lock the piece back into the chuck. Remove the drill chuck from the tailstock and replace it with a live center. This center has ball bearings in it, or roller bearings, that allow the end of the center to rotate freely. So we can lock the tailstock in place with the hand wheel, bring the center firmly into contact with the workpiece, and then lock the tailstock in place. Now we have this part supported both by the chuck and by the center. The pass I'm making this time is the same in depth and speed as the pass that I just made. This time you don't hear the chatter, and if I stop the machine, you can see I have a much better surface finish. The most common way of threading a part is with a die in a die stock like this. I prepared this piece of stock by turning it down to the desired diameter, which in this case is 3/8 of an inch. If I was using this die, We'll just start by pushing the die up against the part and turning the die stock, proceeding down the part to produce the thread. It's a very quick and easy way of producing a thread, but the thread is not particularly accurate in terms of diameter of the thread or also in terms of the straightness of the thread. This die is fairly short, so it tends to wander a little bit as it's cutting the thread. There are times when you want a much more accurate thread than that. In those times, you would typically use a tool like this. If you look closely, you can see the 60-degree angle of a thread is machined into the end of this tool. And this tool is used for single point thread turning. And put the tool in the tool post. Make sure it's perpendicular to the axis of the machine so that the thread ends up being symmetrical in the part. The next step is to couple the feed of the headstock with the feed of the table so that we produce a thread of the desired pitch. To do that, there's a transmission that couples the headstock to the table of the lathe. The first step in setting up the machine here is to select the correct transmission ratio between the headstock of the machine and the table feed in order to produce the desired number of threads per inch. If you look closely here, you can see two sets of numbers. The bottom set of numbers is the number of thousandths of an inch traveled per revolution for cutting. The numbers on top are the equivalent number of threads per inch for that transmission ratio. In our case, we're looking for 24 threads per inch. If I disengage the transmission and move this indicator over until it's in the desired column. Re-engage the transmission. Now coming down this column to 24, come across. Come to B and C. This is another part of the transmission that needs to be set. The A-B knob is here. Set that in the B position. And down here is a knob marked C, D, and E. That knob wants to be set in the C position. Not quite done yet. A couple other levers need to be set. There's a lever here marked belt feed and gear thread. We want to set that in thread, and there's another lever here that also needs to be set in the threading position. Not done yet. There's another lever. Needs to be set. We're going to be making threads that are standard or right-handed. And set that knob in place. We're finally done. This is the most complicated machine that I'm familiar with to set up for threading. You'll find that there are no industry standards for how this is done. Some machines are this complicated, other machines are far more simple, but you'll find no consistency. Some machines have knobs, other machines have levers. They'll put them in different places. Take the time, anytime you're working on a machine unfamiliar to you, to determine the function of all of the controls. And be certain that they're right before turning on the machine and using it in a machining operation. Now, if we come over to the table, we have an indicator here. You can see as I move the table, indicator turning, indicating the relationship between the thread feed screw and the table. Down here, we have a lever marked threads only. You use this lever by setting the forward reverse knob on this particular machine in neutral. Now you find, you push this lever down in certain positions, it will engage the table with the thread feeds. Now let's turn the machine on. Now if you look at what the thread feed indicator is doing now, it's coupled to the screw. So it's indicating that the screw feed is turning. If you look closely, there's a mark here. As the number approaches the mark, you find you're able to engage the thread feed at that point. And you'll feed the thread until you reach the end of the thread and then disengage the feed. At that point, you back the tool out of the thread, back the tool away from the part, and now wait for that number to come around again. And you proceed in that fashion until the thread's complete. Again, there's no consistency from one manufacturer to the next. The safest way to do this is to always use the same number. On many machines, there are some threads that you can cut on any number. There are some other threads that you can cut only on even or odd numbers. And then there are some other threads that can only be cut on a single number. Become thoroughly familiar with the machine before you start experimenting with something like that. Now I'll show you in more detail how to set up the cutting tool to begin the threading procedure. Before we actually start cutting the thread, we've got a little bit more preparation to do. Do this with a parting tool. I'm coming in right up to the shoulder with the parting tool. Then cutting down into the shaft slightly deeper than the depth of the thread. This is called a thread relief, and its purpose is to give me a place where I can stop this tool at the end of a threading pass, take the threading feet out of gear, and then back the tool out. Before we can actually start threading the part, there's one more setup operation that needs to be performed. We need to set the compound to the thread angle, which in this case is 30 degrees. Loosen up the compound and then rotate it. If you look closely here, you can see the degrees marked off on the compound. So rotate this around to 30 degrees and lock it in place. We want to make sure that the threading tool is perpendicular to the axis of rotation of the part. And lock it in place. The purpose of setting the compound at this angle is so that as we're taking deeper and deeper cuts producing these threads, we take those cuts by incrementing the compound in so that we're only cutting on one side of the tool. If we were to increment the tool in during each pass this way with a cross slide, the tool would be attempting to cut on both sides of the thread. And the two chips basically come off and fight each other, and tend to stack up on the tool and damage the threads. So by setting the compound this way and only cutting on one side of the tool, we get a nice clean cut. We can start the machine now. What I'm doing here, you see the tool moving around, is I'm running the cross slide ahead until it comes up against a threading stop. Many machines don't have such a stop. This machine does. It's very convenient. So I run the cross slide up against the threading stop and then bring the tool in with the compound until it just touches the part. I'll back the tool off, look at the setting on the compound. We'll take a relatively light cut. This time we'll take about 5/1000ths of an inch. Now we'll wait until a number comes around to the mark, engage it at 1. This is where threading gets pretty exciting. See the thread being cut? You've got to watch closely and be ready as soon as it runs off the end of the thread to disengage the feed. If you wait a little too long, you stuff the tool into the larger diameter of the part. You shut it off too soon and you damage the back of the thread. Now that it's disengaged, we back the tool out of the part using the cross slide. Back up, bring the tool in, again with a cross slide up against the threading stop. Dial in another 5/1000ths or so. We'll wait for a number to come around. Engage the feed. It's a good idea to keep a hold of this feed engagement lever so you don't have to go looking for it because you don't have much time. So now we've completed another pass, back things out, back it away from the part, bring it again up against the feed stop, dial in another 5/1000ths, and again wait for the number to come around. Engage the feed. Stop. Very easy. Feed after feed after feed, cutting away to lose track of what to do next. Resist the temptation to try to go too fast. What will almost always happen is that you'll goof up the order in which you're doing things. What typically happens if you're in a hurry is you finish a pass, you forget to withdraw this, quick grab a hold of the carriage feed, and you can look here and see what I've done to this thread. It's unlikely that the person using this part will be satisfied with a thread that looks like that. Take your time. This is a relatively tedious operation, but you can expect that. It's also a relatively precise one.